G is equal to K plus P. That's our Cartan decomposition. And then we said that GK has compact type, is practically non-compact type. If the killing form of G on P, respective to P, is negative and non-compact type positive. And then the other type was Euclidean type. If Euclidean form on P was 0, was dead zero. And then remember, in general, yes, this was in general. The killing form of G restricted to the isotropy is always negative. And this was if G mod K is almost effective, which is always part of our assumption. So we assume the space is almost effective. This is always negative, but on P it may be negative, positive, or 0, or mixed. And then we call it compact, non-compact type, and Euclidean type. And then we wrote down several general properties. Let's see, I write them down here. G comma K irreducible implies it has only one type. So either compact, non-compact Euclidean type. G mod K then simply connected implies it's a product. But this is Euclidean type, so compact type and non-compact type. So they're products of these types. So in general, we'll just assume we can, without loss in generality, can we assume that our symmetric space is irreducible? Because otherwise, it's just a product of such things up to coverings. Then, what else do we prove? G compact type. If and only if G and M compact. So M being G mod H, right? G mod K. And this implies G semi-simple. Forget if I mentioned that last time, but this is clear, right? If this has a compact or non-compact type, it's positive, negative on one, it's negative on the other. And the general property also for any type that they're orthogonal. Just because these are the plus and minus one eigenspace and automorphism. So that's always true, this is always true. And compact is negative, non-compact is positive, that means P is not degenerate. So if either one of these types here, these types is not degenerate, of course here it's not. This is not semi-simple.
The type obviously depends on K.
I mean, the symmetric, sure, the symmetric space depends on K, right? The complement P depends on K. In that sense, yes. But once I know the complement of K, it doesn't depend on K anymore. Because on K, once you know the complement P, it doesn't depend on K anymore. Of course, K is the orthogonal complement of P, so implicitly it's certainly part of it. But this is always true, and that's a condition. So it's a condition on P if you want to, on the complement. Of course, here I can always also say if and only if the killing form is strictly negative definite. Similar G is non-compact type. If and only if G and M non-compact.
In that sense, I was going to complain because you say she has a compact type, but it would be intrinsic.
Ah.
Stated with the killing form.
But this is not quite true because, oh yes, for the Euclidean type, G is not compact. So, okay, of course, so this here negative means, since B is negative on K anyway, means it's if and only if B is negative on P, right? And that's compact type. So this also implies G semi-simple. And this is, well, in this case, of course, B is not neither negative nor positive. It's mixed, right? Negative on K, positive on P. Then we had other implications in the compact type. Another consequence was that the sectional curvature of the manifold M is greater or equal to 0. And here the consequence was the sectional curvature of M is smaller or equal to 0. So for each type, it has a fixed sign, greater equal to 0, small equal to 0. Okay, I think that's how far we got. Make sure I don't forget anything. Yes. Okay. By the way, so these are particularly important. This is one possible topic we can go into next after I finish some more of the basics. So these are very important examples. I can come back to that later on why they're important. So another proposition first. G mod K, I think we call it no Euclidean factor. Which means, so in the universal cover G mod K, there's no flat factor. Right, here this says that the universal cover of a symmetric pair is always a product of something flat. Euclidean type is flat. Remember, this was another consequence over here. And this is compact type, non-compact type. So we assume that this one doesn't exist. This always causes problems in formulation of any theorem. Particularly, this proposition wouldn't be true because of examples we saw before. I'll come back to that. So no flat Euclidean factor. That's always a useful assumption. It's not restrictive because of that. So then A, three different statements. A is P comma P is equal to K. So again, we have our Cartan decomposition as usual. Remember, for a symmetric pair, we always have an inclusion. So what this here, so we always have K, P comma P contained in K. Right, this was a property that P is a -1 eigenspace, K is a +1 eigenspace of an automorphism that respects the Killing form. So the brackets have +1 eigenspace. That's always true. This was, in fact, a characterization of being symmetric, essentially. Right? So here, claim equality. Because what does equality mean here? This, strictly speaking, is not a subspace. So by here, I mean the span of all vectors of the form x, y, where x and y lie in P. So that's what I mean by P comma P. Right? If I look at only these B brackets, they're not a linear subspace. So I look at the span of the linear subspace. When I do that, I get all of K. That's an important property. B, the holonomic group, at least the identity component, is the identity component of K. So again, in general, we always had that the holonomic group is contained in K0. This is always true. So we talked about that earlier. But now we claim equality. In fact, these two equalities are very closely related. This is important. Right? This here says we have no idea how small the holonomic group is. So as far as examples of interesting manifold holonomic group, this is not enough. I don't know what they are. Right? Here now tells me what the holonomic group is. Right? And I'll come back to this when I talk a little bit about holonomial groups later on. These are really important examples. So this fact is very important in the theory of holonomial groups. And then C is that the group G is the identity component of the isomorphic group. So remember, this was sometimes caused a problem. If I have a symmetric space, I know that under this group here, I get a symmetric pair. But conversely, if I start with a symmetric pair, it induces a main symmetric space, but we don't know whether G is a full isomorphic group. In fact, for Euclidean type, it wasn't necessarily the case. But if there's no Euclidean factor, then this is always true. Right, let me look at this example again, Euclidean type. It implied in particular that, say, if simply connected, it's isometric to Rn. It's a flat manifold. Because then the full isomorphic group of Rn is all rotations, identity component SON, cross translations. And this was a symmetric pair, so I0 of M SON was then a symmetric pair, as it always is the case. And then the involution, sigma here was sigma of rotation translation was rotation translation by minus B. So that the plus one eigenspace A, that's my SON, and that's my fixed point set. So then I can do the following. I can take any subgroup of SON. I can let G prime be that subgroup cross the translations. Then this clearly takes G prime into G prime again. And of course, the fixed point set is K again. So I get that G prime comma K is also a symmetric pair. But of course, now, so G prime, K is any subgroup of SON, and then G prime is a corresponding group. It's not the full isomorphic group. I can even choose K trivial. Then G prime would only be the translations. That's also a symmetric pair. So C is as false as you want to for Euclidean type. A here, what is P comma P? Well, Euclidean type means it's 0. Right? So again, it's not equal to K as far as false as you want to. And what's Hall 0? So it's the holonomial groups of paths that are null homotopic. And what's the null of a null homotopic path? It must be trivial. Or if you want to, of course, in my space Rn, right? So in Rn, if I translate it on a closed path, I get, let's come back to the trivial one. So Euclidean type, everything is wrong. But that's the only exception. Throw it away, and then everything you want is true. Okay, let's prove that. Is there another one? As we said, P comma P is contained in K. So let's take a vector x in K such that x of all V brackets is 0. So assume this, one is contained in the other, assume they're not equality, then there's something K orthogonal to these brackets. So the goal is to show that x is 0. Of course, I can do this in the Killing form, right? So I know Euclidean type, no Euclidean type means that the Killing form is non-degenerate, so that I can do this for the Killing form. or B of x comma, let's say uv equals 0 for all u comma v in P. So then, as usual, I can use the skew symmetry of the Killing form. Let's say we interchange u and x and v. Doesn't matter. U comma x. Now let me interchange u and x. Sorry. To change u and here put x comma v. So this is equal to 0. For all u, v in P, right? So what does that mean? Well, x is in K, right? V is in P. So where's the Lie bracket, where we had this general relationship, Kp was contained in P. So this whole thing here lies in P. And now the inner product is 0 for everything in P, right? So for all u in P. But B is not degenerate because there are no Euclidean factors. So therefore it implies that the Lie bracket is 0. So notice also the non-degeneracy goes wrong in this example. Right here, what was it? Well, P is equal to the kernel of the Killing form. So the Killing form has a kernel, a large kernel. All of P is a kernel in this case here. So non-degeneracy that I'm using is true because of this assumption here. So what does that mean? It means that all Lie brackets between K and P, sorry, between x and P are equal to 0. So now I can use one of our identities. I can say that, well, then adjoint of x tx applied to the thing in P, so applied to V. This was e to the t ad x applied to V. So brackets of x with anything in P0. V lies in P. This is a power series where I could take repeated Lie brackets with x. So all this lies in P, but in fact Lie bracket is 0. So this must be right, only the first term remains. It must be equal to V. So in the power series, whenever I take Lie bracket, I get 0 because of this here. So the first term is just the identity. So in other words, at x tx restricted to P is identity. But we assume that our symmetric space is almost effective. And the adjoint of things in K is precisely the isotropic representation. So this implies, because almost effective, that x tx is an identity. So if you want to, the kernel of adjoint is an ideal. This here lies in K. So if adjoint had a kernel in here, it would be an ideal in K and in G. The kernel of adjoint is an ideal. That can't be because almost effective means K and G have no ideal in common. So the kernel of adjoint on P is only finite. So therefore, since this is a one-parameter group, it must be trivial. And this implies that x must be equal to 0. Right, if x px is 0 for all t, that means that x is 0. That proves it. So I proved x equal to 0, and that proves this here. Okay, and then the rest also follows easily. So for B, I have to remind you of something. Because it's sufficient to show that the Lie algebra of the Horn-London group is equal to K. Right. I only claim this for the identity component here. So connected groups are the same if and only if the Lie algebras are the same. Right? And there is something that lies in the Lie algebra holonomic group that I discussed at some point, namely, say this for general manifolds, say M is a reminder manifold, so it's a reminder. Then I take the holonomic group at a point. Then if I take U comma V in the tangent space of the point, that implied that the skew-symmetric endomorphism, the curvature endomorphism, is an element of the Lie algebra. This was because this can be described by paratranslation. We had this kind of picture. I take a mesh in the manifold, which at the point P starts in the direction of U for the x coordinate, V for the y coordinate, and then I go here time t, then I go here time t, then I go back. I get a closed path. I paratranslate around the closed path. And then I took the second derivative, and that gives me this curvature endomorphism. So we had pt of V is a path in TPM, and the second derivative of the curvature tensor. It's actually a nice exercise. I don't know if has anyone done that? It's in Docamo. Maybe we can discuss it in one of our problem sessions. It's very, very pretty. And of course, this here lies in the holonomic group. Right? If I take a derivative, I end up in the holonomic Lie algebra. So that's that process. We apply this to a symmetric pair. And then we proved last time what is the curvature tensor of a symmetric pair. Sorry. It was the triple Lie bracket up to a sign whenever U and V and W were in P. And this identifies as usual with the tangent space at the base point. So in other words, RUV, the one that lies in the holonomic Lie algebra, is simply a bracket. So I can say RUV is the adjoint of the Lie bracket between U and V as an endomorphism from P to P. So this means this lies in the holonomic group. In the Lie algebra of the holonomic group. And now we just saw that U comma V is equal to K. So here I can achieve, by possibly adding things if necessary, add of anything in K. So by part A. Right? And that's what it says, right? So I wanted to claim that they have the same Lie algebra.
Again, the almost
Say it again?
we don't have that in the Lie-Algebra case.
Unless it's almost effective, yes. That's part A. But I'm now using part A here. This is by A. And A was only true when it's almost effective.
But the Lie-Algebra of the holonomic at this point is adjoint of K.
So what is K? So how do I mean that it's equal to K? So what do I mean by this? I have to interpret this. They both act on the tangent space at the base point. How do they act? This acts by definition, just paratranslation. And this here acts, so K acts by adjoint. Okay. So if I talk about the real algebra of K, this is equal to Rx, the span of Rx, where x lies in K, acting as an element of the endomorphism of the tangent space of P. Right. So as such, I can identify it with something in the Horn-Lombardy algebra. Okay. So here it's really all of Rx for x lies in K. Because you're right, it might be 0. If it's not almost effective, then this could be 0 for some x in K, whatever lies in the common ideal. That's true. But this equality certainly is always true. Okay, so that implies B. So it's really easy as long as I have this understanding of non-compact and compact type. C also follows easily now, as something we've done before. So I start with a symmetric pair. Then I let G prime be the full isometry group of the manifold. And then K prime the stabilizer of the full isometry group at my base point. And then we know that G prime, K prime is also a symmetric pair. And of course, G is contained in G prime, and K is contained in K prime, since they also act by isometries. And then we proved something last time, so recall, if sigma prime is the automorphism of G prime, that makes it into a symmetric pair. So G prime, sigma prime is this identical component, the same thing as K, but in mutual symmetric pair notation. So there's an automorphism, involutive automorphism for the pair G, K itself by definition, and another one for the pair where I take the full isometry group. And then what I want to recall is that sigma prime, we show that sigma prime takes G to G. So sigma prime is equal to sigma restricted to, sigma restricted to G is sigma. Right, well, sigma is my involution of the symmetric pair. So that means the following. So we write for G, we have K plus P. That's our Cartan decomposition. I have another one for the full isometry group. And what does this here mean? Well, K and P are the plus and minus eigenspace of the derivative of the automorphisms. That means that they must be contained in each other. So K is contained in K prime. Well, that's of course immediate from this here. But the important fact is that P is contained in P prime. That, in general, is not so obvious. And that follows from this fact right here. So at some point we talked about this last week. Okay, so now let's use that. So I have a second symmetric pair, G prime or K prime, and this is also has no Euclidean factor. Because the Euclidean factor means geometrically, when you merge a couple of manifolds, something flat splits off. Because the manifold's the same. I just represent it in two different ways. So this also has nothing flat splitting off. That means I can apply part A also to P prime. Well, I also know that P comma P is equal to K, because that was a symmetric pair. So what does that mean? We had another consequence, right? So P was contained in P prime. And then our next observation was that, well, they have the same dimension. Right? P is the dimension of the manifold. So therefore, they had to be equal to each other. So that was the... I think we used that argument when we computed the geodesic as a symmetric space. So in addition, I have that P is equal to P prime, which means these two are the same. And that means that K and K prime are the same. Well, if P is the same and K is the same, that means that G prime is equal to G. And now you're done, right? Only K. These are both connected. So G is always, in this notation, G is always assumed to be connected when I talk about a symmetric pair. So they have the same D algebra, so therefore they're the same. So now in all the examples we discussed last week, I've now computed at least the identical component of the isomorphism group. Right? In general, that's a difficult thing to do. If I give you a manifold and want to compute the isomorphism group, there's really no good technique to do that. It's very difficult in general. Here, it's true for any symmetric pair as long as there's no Euclidean factor. Okay. Let me maybe mention now the application of this to Hall-Norming groups. There's a beautiful theorem due to Berger, which says the following. So this is a Riemannian manifold with an Hall-Norming group Hall. Of course, an Hall zero identity component. I'm dropping the foot point now because we know they're all isomorphic if I take different foot points. And the conclusion is that either M is isometric to a symmetric space, okay, I should assume irreducible. And just to make sure I'm not missing something, let's assume simply connected. And what we call indecomposable. A bit earlier, so not a product. As a Riemannian manifold, I can write it as a Riemannian product of two manifolds. That's not restrictive because if there is in the Hall-Norming group splits up as a product of two groups. So if you want to classify Hall-Norming groups, I might as well do it for those manifolds which aren't product of two other things. Simply connected, I don't think is so important as long because a manifold in its universal cover, they might have different Hall-Norming groups, but at least the identical component is the same. So in this theorem, this assumption is not so important. Either M is isometric symmetric space, and in that case, K0, Hall 0 is equal to K0, which was a stabilizer of the isomorphic group. I guess maybe I should maybe exclude the case a priori where the manifold is flat, where this group is trivial. Right? So that's, of course, another possibility, so indecomposable and not flat. Again, that's not a strong assumption because if it's flat, I know that Hall 0 at least is trivial. Okay, so either it's symmetric space, and then by this theorem over there, Hall 0 must be K0 of the symmetric pair, and since the G is identical with the isomorphic group, K0 is also just the identity component of all isometries fixing the point of the stabilizer. And I'm combining both B and C for a symmetric space. So in this case, so either I mean in this case where I understand now what happens, it's a symmetric space, so very nice isometric to it, right? So the metric itself is also symmetric, not just the manifold, not just the group is that. The metric is that also. So very rigid. It's really rigid. Or Hall acts transitively on the unit sphere inside the tangent space. Right, so Hall here is the Hall-Nommer group at that point. Right? So it means acts on the tangent space via isometries, by translation isometries. So it acts only by isometries, that means it acts also on unit sphere. And I'm saying that that action must be transitive on the sphere. So that's really special. This theorem has a long history. Originally, this was Marcel Berger's PhD thesis, and it was a somewhat unpleasant proof in the sense that he classified. So after a long discussion, he classified all the possible groups Hall 0. And you get a long list, and you observe, well, it's the same list as the symmetric spaces, except for these groups that are transitive on spheres. By now, there are more conceptual proofs that don't use classification. So, but what about part B? So how big is part B?
So essentially, it is always as big as possible.
No. That's because of the foreign proposition. So part B, you might think, well, it's a full orthogon group. But that's not the case. Okay. So if G contained in SON acts transitively on Sn minus 1, say contained in Rn. So it acts by rotation on a unit sphere in just in fixed Euclidean vector space. It acts transitively. Then it is one of the following. And I'm going to write down the group G. I'm going to write down the pair G and the stabilizer of some point. So, for example, the North Pole. So we write as G comma K, such that G comma K is not a sphere. It will be the same thing as saying that the group acts transitively. So in other words, the question now is, in how many ways can I write a sphere as a homogeneous space? Not as a symmetric space, right? In fact, we already saw from the theory, well, the sphere is irreducible, right? So I can write it as a symmetric space in only one form. The full isometric group has only one symmetric pair that describes the round sphere. But now forget about symmetric pairs. Ask the question, in how many ways can I write as any homogeneous space? And it's one of the following. So part A, so I'm going to write down the pairs. Certain obvious pair is the full group. And then the stabilizer is SON minus 1. That's the standard where you write a sphere as a homogeneous space, the one you would think of. Of course, then the whole unit group is everything, right? Everything in SOK, and it is some pair translation for some closed path. That's some of the generic thing you might expect. That if the manifold is generic, there's lots of curvature. If there's lots of curvature, then these curvature endomorphisms I wrote down earlier, they're complicated. They lie in the whole Lie algebra. If they're complicated enough, they span the whole orthogon group. Right? So that's a generic case. Other case is U n over 2, U n over 2 minus 1. So if n is even, of course, if n is, sorry. Well, let me do it like this. Un minus 1 acting on Cn, so that's a sphere S2n minus 1 inside Cn. So I think we talked about this transitive action before also. Right, that's how we compute the fundamental group of the unitary groups. And then I can also look at the subgroup SUN minus 1. That also acts transitively on the same sphere. And we saw another one when we computed the fundamental groups of the symplectic groups. So this acts on a sphere of dimension 4n minus 1, sitting inside Hn. Tautological action, that's transitive. That's a stabilizer. I can do a little bit more. Namely, I can let Spn times Sp1 act. And the stabilizer is Spn minus 1 times diagonal Sp1. Again, acting on the same thing. So here, I'm extending this action in a certain way. So how does this act? Let me describe it. So I take an element A, comma Q. A is a quaternion matrix. Q is a quaternion. I want to let it act from Hn to Hn. It's supposed to act on Hn. So I take a vector V. I send it to A times V, a matrix multiplication. Then I multiply with Q inverse on the right. Now, so remember the quaternions aren't commutative. So Q inverse on the right is different from Q inverse on the left. But this, for A, I could take Q times identity. That would be left multiplication by Q on the vector V, on the quaternion vector. But that's in general different from right multiplication by Q. So this really adds something in addition than SPN. It adds something extra. So these are from the classical Lie groups, E, and now there are three more. G2, SU2, acting on R7, which we wrote as imaginary Cayley numbers. So the G2 was the automorphisms of the Cayley numbers. They preserve the imaginary part. They were orthogonal, so they lie in SO7. So here G2 I regard as lying in SO7. And that acts transitively on the imaginary Cayley numbers. That's something you proved at one point. And the stabilizer was SU2. So here I can say, well, S6 I can write as G2 mod SU2. It's a very funny way of writing down the sixth sphere of the homogeneous space. There are two more. They also involve exceptional Lie groups. C, D, E, F, G, H. G is spin 7 mod G2, acting on S7. Sitting inside the whole Cayley numbers. We haven't discussed the spin groups. I'm not going to say much about it, but of course this here is 8-dimensional, so this is spin 7 contained in SO8. And that's a spin representation. One of the low-dimensional spin representations. So it acts on R8, and then it turns out the stabilizer is G2. B, C, F, G, H. One more. Another spin group. Spin 9, comma spin 7. Because by the way, here maybe I should write this down. This means that S7 is spin 7 mod G2. So a funny way of writing S7 as a homogeneous space. Okay. So this acts on what? Acts on S15 inside R16, which I can write as Cayley numbers plus Cayley numbers. Again, I won't write down the action, but so on the one hand, I can say, well, spin 9 sits inside SO16. That's what it means to act on S15, on 16. And that's a spin representation again. And then the claim is a stabilizer spin 7. So spin 9 mod spin 7. It's a funny way of writing down the 15th theory. Okay. That's it. So transitive actions on spheres are special. There aren't that many, but it is an interesting list. It's not just the classical ones, there are also the 3 exceptional ones. Now, what Berger didn't prove or didn't show that these groups actually all occur as the holonomic group of some Riemann manifold. So he just classified and observed either it's in the classification of symmetric spaces, you just check Harrison, whatever, right? And this classification of transaction on spheres is also fairly old. This is Borel in the 50s, I think. And then he observed the rest belongs to these transitive actions. So it means the holonomic reduces, right? So here, the manifold itself would have to be 7-dimensional, and the tangent space 7-dimensional. This is a full orthogon group, and the holonomic is a subgroup equal to G2, and so on. Each one of these, except for part A here, have special geometries associated to them. And if you want to, we can talk about more about that at some point. Right now, I don't want to say too much. This, for example, are Kähler manifolds. These are Cayley manifolds where Ricci is 0. These are Guccione-Kähler. These are Ricci flat. These are Ricci flat. These are Ricci flat. This one here, one can eliminate because the manifold itself, in this case, has to be isometric to the Cayley plane. So there's only one Riemann manifold that fits into this category of holonomic group H. So as far as the list is concerned, one could eliminate because it's all in part A. This only occurs for a symmetric space. Then one can say that this is called hyperkähler, Guccione-Kähler. This is called hyperkähler. Again, very special geometries. Analogs of Kähler and Kähler-Ricci flat, but very much more rigid. And I forgot one case, let me call it E prime, at least in Borel's theorem, which says I could also, instead of multiplying on the right by the full quaternion group, by only a circle sitting inside SP1. So in other words, I can say, well, the transitive action of SP under the sphere I can extend to a 3-dimensional bigger group or to something inside there. Since SP and or they act transitively, of course, both this group and this group are transitive. But this is another possibility of, say, as a pair, G, K. It's a different pair, right? Then it turns out that if one looks at holonomic groups, in fact, if something is of this type, it must be of this type. So again, this can be eliminated. So in a way, one can eventually throw out E and one can throw out H because they ought to contain the rest of the other list somehow. Not eliminate as transitive actions, they are transitive actions, but at least eliminate as part B in the holonomic theorem. Okay. Then it took a long time to actually show that all these groups can be holonomic groups of a Riemann manifold. That's a long history. Because these are classical, so these are easy. These came a little bit later that such things exist, and these exceptional holonomic groups are particularly interesting. So F and G here, they are studied a lot more recently. Have to do with many other subjects. But say, for example, that the compact manifolds where G2 is a holonomy group, that's only maybe 10 years old. It's not that old. They're difficult to construct. Okay, so these symmetric examples are very important. Right, so that's one possibility of a holonomy group. Either it's very special. Generically, it's a full orthogonal group. Then you can't say anything else. Right? Or it's one of these groups, which then means there are very special geometries associated to it, like Kähler or Kähler flat or hyperkähler and so on. That means there's a very special geometry. Still flabby in the sense that there are many examples. They aren't rigid. Like part A here, this is completely rigid. It must be asymmetric to symmetric space. So these are flabby, but nevertheless very special geometries. And then even these symmetric spaces. In a way, these are the smallest holonomy groups there are. They're smaller than these examples over there. Okay, so theory of symmetric spaces is important for this kind of classification theorem. This theorem right here is a purely topological theorem. It's not so easy to prove. In fact, the way Borel proved this is just pure topology. So he studied homogeneous space G mod K, which has the same homology of a sphere. So just an algebraic assumption, simply connected and the same homology as a sphere. Then he classifies the pair G, K by using things in algebraic topology, classifying spaces, spectral sequences, all kinds of things enter in order to then prove that the pair all looks like this. They all look like this. So that's difficult algebraic topology here. And okay, so that's just to put everything into context. So this is something we could talk about more at some point later on. One more topic I want to discuss today is what I mentioned last, the matter of duality. Between compact and non-compact type. So by the way, these theorems I didn't put into the notes yet, these polynomial theorems. So this goes as follows. So let's say I have G, K, a symmetric pair. No assumption here of type or anything. So then I have my Cartard decomposition. And now I define G prime as K direct sum IP inside the complexification of G. Right. So this as a real subalgebra. So as a real subspace for the moment. Not as a complex one. Of course, complex span of that would be all G tends to C, clearly. Just look at this as a real subspace. And now observe the following, that G prime is indeed a real Lie algebra. And that's very special. Of this complex Lie algebra regarded as a real Lie algebra. Right? That's what the notation we did had in the complexify. Like it's a real Lie algebra. That's a real subspace certainly, and I claim it's a real Lie subalgebra. To see this, I use my relationships that I know for the Cartan decomposition. These hold if I have a symmetric pair. So that's part of this conclusion for this Cartan decomposition. So now just observe that, well, what's IP That's minus p comma p. So that's contained in K. KIP is I times K comma P. K comma P lies in P, so it's contained in I times P. And of course I have this, so KK in K, IP in K, and KIP in IP. So brackets here lies in here, brackets here lie in there, brackets here lie in here. The sign change doesn't matter. What's the subalgebra? Right? Notice that what's crucial, so this of course is just a subalgebra. This is no big deal either. It's because it follows right from here. That just means that the decomposition is reductive. Right? For every Lie algebra, I can find a component like this. That, of course, would imply this here. No big deal. This here is the important relationship. And, of course, this here was important. That comes from a symmetric pair. So this here is very much based on the fact that I start with a symmetric pair. That makes this into a Lie subalgebra. Otherwise, it wouldn't be one. So now, I let G prime be the unique simply connected Lie group with Lie algebra G prime. And K inside G prime, the subgroup, connected subgroup with Lie algebra K. And K by definition sits in G prime. I didn't change K. K didn't change. Well, we should call it K prime. At the moment, possibly a different K. So then I can look at, then I claim that G prime K prime is also a symmetric pair. So why is that? Well, here I have my automorphism, which makes this into a symmetric pair. So that means that D sigma is an automorphism of G. So these are plus and minus 1 eigenspaces. So I can complexify. That now becomes an automorphism of the complexification. And now I observe that it preserves G prime. Right, what's G prime? Just K plus IP. Automorphism is plus identity here, minus identity here. So when I complexify here, it still preserves K, and IP here it's plus identity, it's minus identity. So and defines involution sigma prime from G prime to G prime with stabilizer equal to K prime, at least identity component. Right, so I have an automorphism of complexification. It preserves the G's. I have an automorphism of G prime. G prime is simply connected. That means it extends uniquely to an automorphism of the Lie group, whose derivative is that automorphism. So that's how I got my sigma prime. And of course, what's the identity component? At least I can tell from the Lie algebra what's fixed by the Lie algebra by D sigma prime. Well, that's precisely K. Here it's minus identity again. So that makes this into a symmetric pair for this involution sigma prime. So that's my duality. So I start with a symmetric pair, G comma K. I define G prime comma K prime. That's a new symmetric pair. And I can essentially go backwards. So what happens if I start with G prime K prime? So then I would have my G prime K plus IP. I multiply with I, and I get back K plus P. So I come back to the original symmetric pair. With this small proviso, well, it's certainly the same Lie algebra, but maybe this is not simply connected. I might start with a symmetric pair where this is not simply connected. My construction of duality, here it was important that I let G prime be the simply connected Lie group, such that this is uniquely defined, because it's only defined in the Lie algebra. So I can go backwards, but only the same G up to covers. In other words, if I go back here, then by construction, my new group would be simply connected, which means there was a cover of G. Right? So if I go backwards, maybe I should say it this way, I get G tilde, K tilde. So up to that, it's a one-to-one correspondence. Particularly, I can say that maybe I don't want to say that yet. Notice that if G, K is compact type, this implies the dual is non-compact type. Is compact non-compact type, and conversely. So if it's compact, dual is non-compact. If it's non-compact, the dual is compact. There's a precise duality. So why is this? Let's say this is a compact type. This means that the killing form on P is negative. Well, so that's what's the killing form of G prime? So killing form of G itself. That's negative on K always. Negative on P means compact type. G prime sits inside the complexification. How is the killing form of the complexification related? So this was an exercise at some point. Well, that's the killing form of G tensor C. Which is the same thing as G prime tensor C, and then restricted to G prime. So maybe this, of course, yeah. That's a general fact for complexification of Lie algebras. I have a real Lie algebra, it has a killing form. I complexify, it has a killing form. When I restrict, I get the killing form back. So what's B restricted to P prime then? Well, that would be the killing form on the complexification of IX, where X lies in P. Well, that's minus BG tensor C of X comma X. This is positive, so this one is negative. Okay. So just because I multiply by I in P, that changes the sign of the killing form. Because I can, computing it in here is the same thing as computing the complexification for G, then by restricting also for G prime. But now it changes the sign of the killing form. So it takes non-compact to compact type, and if GK has Euclidean type, then the dual also. So why is that? Well, what does Euclidean type mean? It just meant that P comma P is 0, all the brackets are 0 in P. Well, then IP is also 0. So the Euclidean type, again, is uninteresting, right? The dual is just itself. So what? So this, again, the ones with no Euclidean factor, the interesting one, then I get a nice duality in compact and non-compact type. Example. Let's use this right here. Particularly if I want to classify, I can classify either type. Doesn't matter. and I classify the dual type also. As far as classification is concerned, the compact type is easier to classify. So I can do an example later on of how one classifies. But example of duality. So I think I mentioned at some point the most basic case is hyperbolic space and the sphere are dual to each other. Okay. Of course, this here was SON plus 1 dot SON. That's a symmetric pair. And this here was SON comma 1 mod SON. That was a symmetric pair. This here is non-compact, and this group was compact. Right? So that's supposed duality. More generally, I can look at the Grassmannians here. So see what are K-planes in Rn, I think we wrote it. Let's look at oriented ones. This was SON divided by SOK, SON minus K. So of course this is a special case when K is equal to 1. So more general. And then the dual of that is supposed to be SOK comma n minus K divided by SOK SON minus K. So again, this group is compact. This group is non-compact. So that's my compact type 1. That's my non-compact type 1. We saw both of these as symmetric pairs when we did examples earlier. So let's see why this is indeed the dual. So let's start this with a compact pair. So this is a compact type. And sigma was conjugation by what we call IPQ, sorry, IKn minus K. So this was a matrix which had 1, 1, minus 1, minus 1 over the diagonal. First K1, last n minus K minus 1. So when you write things in block form, what did I do? So multiply on the left, well here it does nothing, right? So minus 1, on the right minus 1. See here, in the first rows I multiply minus 1, minus 1. It's left multiplication by that matrix. Right multiplication does it with the columns. Nothing in the first columns, minus 1 in the last columns. So here it does nothing. So change the sign according to that pattern. Right? So then what was the stabilizer, say on the Lie algebra level, was things of the form X must be skew symmetric, so it must be X minus transpose, where X is any n by n matrix. Sorry, this was P. A comma B, that's a plus 1 eigenspace, right? Where A comma B are skew symmetric. And what's the minus 1 eigenspace? So then this must be 0. That's a minus 1 eigenspace. And then it looks like 0, 0, x minus x transpose. And now x can be anything. K by n minus k. So that's my Cartan decomposition of this symmetric space of compact type. By the way, we now proved that SON is the identical point isomorphic growth of the Grassmannian, right? That's what we proved today. non-trivial fact. So what is on the dual? It doesn't quite work on the dot. So if I take this pair SO k comma n minus k, SO k cross SO n minus k, this was a symmetric pair of non-compact type, because the group is non-compact. And the involution was, again, conjugation was the same thing. So again, the same pattern, right? Plus 1 minus 1 plus 1. So then what is k? Plus 1 eigenspace, so again, sits inside here, sits inside here. And what does that mean? So this here was an inner product, which is a positive definite on the first k, negative definite on the last n minus k. So this matrix right here must respect the positive or negative definite inner product on the first k coordinate. So it must be the Lie orthogonal group, so it's Q-symmetric. Same thing as the last one. That's K. What's P? Okay, there must be something here, a certain X here. Now the question is what goes down here. They are not quite skew-symmetric. So what was the definition of the Lie algebra of SO k comma n minus k? These were matrices, should I call them R maybe? N by n matrices, such that R I k n minus k plus I k n minus k R transpose is 0. Right? If there's no I, that's skew-symmetric. And if I put an I there, that's the Lie algebra of this indefinite inner product Lie group. So it's skew-symmetric, except I have to multiply by minus sign, and I claim the effect is that this should be X transpose for this any matrix. Right, so it multiplies by minus 1, where was it, in the last k coordinates. One's on the left, one on the right. One on the right doesn't do anything because that's a 0. On the left multiplies this with a minus sign. So instead of Q-symmetric, it must be X, minus X must be X transpose. So it doesn't quite work out yet, right? I times, let's call that P prime, or it's a new one, right? This is K prime, this is P prime for my symmetric space, symmetric pair here if you want to. K is K prime. That's okay, right? What are we supposed to do? We're supposed to multiply by I. So K is equal to K prime, but I times P is not equal to P prime. So it doesn't quite work out yet, but I claim it's okay up to conjugacy. So by this I want to look at conjugate with the matrix which has following entries. I have to do it right. I. And I claim this will take K to K. Of course, that's K prime. So it preserves both of them. And it takes IP to P prime. So if I call this alpha, I claim alpha is an automorphism of the complexification. Right? Complex entries, you have to complexify before it comes automorphism. And I claim alpha of G is equal to G prime. So they are dual to each other up to an automorphism. So to take this to this, I certainly can't do it with multiplication by I, but I claim up to an automorphism I can do it. So let's check this. So what happens if I take such a matrix, 0x minus x transpose, and I conjugate with such a matrix. So let's do it left first. On the left, I multiply the first rows by I. Sorry, the first rows by I. The next rows by -1. So that's on the left. Now I multiply with this matrix on the right. Now it works in the columns. So multiply the first columns by I. And then multiply the last columns by -1. Pardon? Say it again. This on the left, right? Pardon? If I multiply the matrix with the diagonal matrix on the left, I multiply the rows.
It's not an evolution, so we change the sign of I.
I'm not saying it's an evolution. That's true. I'm saying some automorphism on the classification which takes one G to G prime. I just want to show that they're isomorphic to each other as Lie algebras. Right? So it takes this automorphism takes G comma K into G prime comma K, which is K prime. That's what alpha does. So it's just another way of looking at the same symmetric pair.
Yes, only the action we multiply on the left by that matrix and on the right by minus.
Yes. Which changes the sign of I. Good. We probably need that now. Then we get what? And here an IX. Is that what I want? Minus IX. And that's an element in P prime. Right. This is a transfer of this, but no sign change. That's what P prime says. So this is an element in P prime, whereas here it's an element in P. So alpha conjugation by this matrix takes P to P prime. Of course, on these diagonal entries, it doesn't do anything because here it multiplies by this entry by I, then by I inverse, so it cancels. This one by -1, then by -1 inverse, so it cancels. So if I think of these diagonal entries, alpha doesn't do anything. So indeed, it takes K to K prime. But on P, it has this funny effect that it takes P to P prime. So here it doesn't quite work on the nose, but up to automorphism, indeed, that's a dual. So that's one duality. Okay. Okay, one more remark is, remember what's the curvature of UVW? That's minus UV bracket W. So what's R prime? Well, for this I have to take IV, IU, IV, IW. Well, that's plus the Lie bracket of UVW. So it's the curvature tends to the same, it just changes the sign. Particularly if I think of the section curvature, say of a two-plane spanned by U and V, that's minus the section curvature prime spanned by IU, IV in the dual pair. The curvature just changes by sign. So also the geometry is very, very similar between a symmetric space and its dual. It's good to see some more examples. I think I have 2 more examples in the notes. I'll see if I want to do it on Wednesday or not. The one that's kind of funny is what's the dual of K cross K, diagonal K. The compact Lie group I can write as a symmetric space, and as a symmetric pair it becomes K cross K, diagonal K. What's the dual? That's a little tricky. Like I claim what it is. I do the following. I complexify the Lie group, then regard it as a real Lie group, and K sits inside it. So how do I complexify a Lie group? So it's a natural process that I could exactly complexify the Lie algebra. It becomes a properties Lie algebra. Then there's a unique Lie group associated to that. It's complex. That's what I mean by KC. Right? And now forget about the complex structure and it becomes a real Lie group. And K certainly sits inside this group as the real points. And that's supposed to be a symmetric pair. So for every compact Lie algebra, this is a symmetric pair. And that's my non-compact dual. This here is my compact space. So that's a kind of funny example of a duality. Okay. On Wednesday, I'll do a few more topics just to finish the basic theory. And then we should decide on what kind of things you want to hear about. So we could do some holonomic groups. We could do some symmetric space of non-compact type. They have lots of very special properties. We can do Hermitian symmetric spaces. So these are examples of Kähler manifolds. Then we can do some what are called quaternionic symmetric spaces. They're closely connected to this other example of holonomy that was an SPN SP1. So analog of Hermitian symmetric is quaternionic symmetric. And then we can also talk about the topology of symmetric spaces. So one can say lots of nice things about like what the Durham cohomology of a symmetric space is, for example. So these are all topics we could cover and point out all of them since there's only, 3 weeks left maybe? So there's about 3 weeks left, I think. So we can't cover all those topics. And you might want to think about which one you want to hear. On Wednesday, I can say a few things about each one, a little more detail. And then you should tell me what you want me to start next week. Okay. In the notes, I do a little bit of Hermitian symmetric spaces and symmetric space of non-compact type and topology. I don't have anything in